everybody, and welcome to the Malate Aspartate Shuttle video. This video is all about the other way we have of getting the hydrogens from NADH that came from glycolysis out in the cytoplasm. So here it says cytosol, cytoplasm is the same thing, they are synonyms for each other. So how do we get this hydrogen from the NADH into the mitochondria? Just like how we did with the glycerol phosphate shuttle. But here's going to be a little bit of a different process, because with the glycerol phosphate shuttle we were really just taking the electrons, the hydrogens, from the NADH and crossing them over. Here we're going to be taking an actual molecule called malate and moving it across the mitochondrial membrane. So we're going to need to be using a transport mechanism. Just like we have on cell membranes. So just to refresh your memory about transport mechanisms on cell membranes, this would be the same way that they work on mitochondrial membranes, like we're going to be talking about here. But if you have a membrane, double layer membrane, where cell membrane or mitochondrial membrane, and a little protein channel embedded in that membrane, and we can have one molecule move in either in or out of wherever we're talking about through that channel. We could have two molecules moving. Maybe they're going in the same direction. Maybe they're both moving, say, out. Or we can have two molecules moving in an opposite direction. Or this could be more than two. If we have one, we would call it a uniporter. So one molecule moving, you would have seen this in like a sodium channel. You open a sodium channel and sodium goes into the cell, something like that. Here we have two or more molecules moving in the same direction. This would be a symporter. And here we have two molecules moving in an opposite direction. This would be an antiporter. So you've seen an antiporter a zillion times by now, I'm sure, in the form of the sodium-potassium pump. Sodium moving one way, potassium moving another. And we're going to see some antiporters here in the malate aspartate shuttle, but on the mitochondrial membrane instead of, on the cell membrane like the sodium-potassium pump would be. So just the general overview for our malate aspartate shuttle is that we're trying to take the hydrogens from NADH, and we're trying to get them into the mitochondria so that we can use those hydrogens, the electrons from the hydrogens, in the electron transport chain. So that'll go to the electron transport chain. And in order to do that, we just are essentially going to take those hydrogens off of the NADH, put them onto oxaloacetate, which is this molecule out here in the cytoplasm. So we're going to add a hydrogen, taking it away from NADH. So we are reducing oxaloacetate while we oxidize NADH into NAD. That reduced oxaloacetate with that new hydrogen on is malate. So malate is going to cross the mitochondrial membrane, going into the mitochondria, but it's moving in exchange with another molecule called alpha-ketoglutarate. That alpha-ketoglutarate is going to be leaving the mitochondria. So malate is going in, alpha-ketoglutarate is going into the cytoplasm, so it's moving out of the mitochondria. So now we have alpha-ketoglutarate out here. So keep your eye on the alpha-ketoglutarate. We're going to get back to the alpha-ketoglutarate. This is a molecule that we are going to see a million times this semester. We've seen it in the Krebs cycle before. So here we have our Krebs cycle. There's alpha-ketoglutarate as part of the Krebs cycle. But it's also part of this malate aspartate shuttle. It's useful for helping to transport the malate in as the alpha-ketoglutarate goes out, thanks to this antiporter right here. So then we're going to take this malate that is now inside the mitochondria. It has that hydrogen, and it's going to take that hydrogen, there goes the hydrogen, and the hydrogen is going to be added to NAD+ that is in the mitochondria already, forming NADH, and off to the electron transport chain with those electrons as part of that hydrogen. So that's the whole purpose. That's what we were doing this for, trying to get the hydrogens from NADH over here onto malate, onto NAD+, so that we can have NADH and go to the electron transport chain. But we need to complete our circle. So we've done our main point, our main goal, which was to get those electrons off to the electron transport chain, but now we need to reset, essentially. So to get ourselves back to where we don't just have dehydrogenated malate, which is oxaloacetate. We took the hydrogen off of the malate here, and now we have oxaloacetate again. But we don't just want to leave that here, although oxaloacetate also part of the Krebs cycle over here. So, but we want to be able to get that back out into the cytoplasm again, and oxaloacetate can't just cross the mitochondrial membrane. So we need to convert that into aspartate, which we'll get into the details of that in a minute or two. And that aspartate is going to move out of the mitochondria across that membrane. We're going to have another antiporter here. But now we are trading the aspartate for a molecule called glutamate. So glutamate goes in to the mitochondria while aspartate goes out. So now we have glutamate inside the mitochondria where it used to be outside the mitochondria. Okay, so keeping glutamate and alpha-ketoglutarate kind of in the back of your mind, set them aside for a second in your mind, and we'll just look at the main circle here, the main part of the shuttle, where glutamate and alpha-ketoglutarate are part of that, but a little bit outside of it. They're a little bit separate. They're tied to it, but they are not part of the three main molecules that are turning into each other, we should say. So if we start here, let's just call that like number one. It's a circle, so you could technically call any part of it number one, but we're going to start with oxaloacetate. We've got oxaloacetate, we add a hydrogen to it, we get malate. We move malate across, trading for alpha-ketoglutarate, but we get our malate across into the mitochondria, then we take that hydrogen off again, and we get our oxaloacetate. In the meanwhile forming NADH for the electron transport chain. But we have oxaloacetate again. So now we've just reversed. So over here we take oxaloacetate, turn it into malate. Over here in the mitochondria we're going to take malate and turn it into oxaloacetate. So it's just a reversal of the reaction. And we are taking hydrogens at this point. We're just moving a hydrogen from one place to the other. So the enzymes that move hydrogens are always going to be called, or I shouldn't say always, never say always, but oftentimes the enzymes that remove a hydrogen from one molecule, whether we're taking it away from NADH or whether we're taking it away from malate, the enzyme would be called a dehydrogenase. So dehydrogenases remove hydrogen from a molecule so that it can be put onto another molecule along with its electrons. Okay, so then we're going to convert the oxaloacetate into aspartate. Aspartate gets transported out of the mitochondria, so now we're back in the cytoplasm, and we're going to take the aspartate and turn it back into oxaloacetate. So again, another kind of reversible reaction here. So where we have oxaloacetate turning into aspartate, then we have aspartate turning into oxaloacetate. So it's really just two reversible reactions involving three molecules. Just this side in the cytoplasm we're going in one direction, and then in the mitochondria we're going in the other direction. Then we can start to think about glutamate and alpha-ketoglutarate and what they're doing. And what they're doing is just being involved in one, antiporting the malate and antiporting the aspartate, so helping to get the malate in to the mitochondria and the aspartate out of the mitochondria. But they are also donating and accepting amino acids in order to help with the transformations along the way. So let's look at the enzymes that do that. We already saw dehydrogenases. That's what takes hydrogens away from one thing and puts them onto another. We can also do this same kind of thing with amino acids, where we transfer one amino acids from a molecule, or we take an amino acid from one molecule and transfer it onto another, is a better way of saying that. And the enzymes that do that tend to be called Amino Transferases. So they transfer amino acids from one molecule to another. So essentially one molecule is going to be donating an amino acid, one molecule will be accepting the amino acid, one molecule will be aminated. So amination means adding an amino acid to something. If you take the amino acid away, that's deamination. So you're removing an amino acid. And, you know, those are paired together. If you deaminate something and you aminate another thing, you have just transaminated. So you're moving an amino acid from one molecule to another. And this is what we are going to have happening between the glutamate and the alpha-ketoglutarate, involving also oxaloacetate and aspartate. So this is where it gets a little bit confusing, where we start to think about these amino acids also moving around. The hydrogens are kind of easy to remember. You know, you add a hydrogen onto oxaloacetate, you get malate. You take the hydrogen away from malate, you get oxaloacetate. For the amino acids moving around, it really is just the same thing, but I've sort of simplified it by writing it out here. Our glutamate, glutamate is going to give the amino acid, so it's going to be deaminated. So we're taking away an amino acid from the glutamate and we're giving it to oxaloacetate. So we're just essentially taking the amino acid off the glutamate, putting it onto aspartate, or putting it onto oxaloacetate. And that will cause us to form aspartate. Okay, so glutamate loses the amino acid, gives it to oxaloacetate, now we have aspartate. But what is left is this deaminated glutamate. So glutamate is like, okay, I don't have my amino acid anymore, now I am alpha-ketoglutarate. So alpha-ketoglutarate is just deaminated glutamate. If we animated the alpha-ketoglutarate, then we get glutamate again. So just to show that that can go either direction. We take away the amino acid from glutamate, we get alpha-ketoglutarate. We put an amino acid onto alpha-ketoglutarate, and we get glutamate again. Now in the mitochondria, we're not doing that. We are not going to reanimate the alpha-ketoglutarate into glutamate. We are simply taking the amino acid, off of glutamate, putting it onto oxaloacetate, we form then aspartate, leaving us with this deaminated alpha-ketoglutarate. Where are we going to do the opposite? See if we can see them both here. Once that aspartate, so remember the aspartate has that amino acid from the glutamate, it's going to give that amino acid to the alpha-ketoglutarate that is out in the cytoplasm, once we're out in the cytoplasm. So then we are just back to oxaloacetate. We took away the amino acid from aspartate. So we're just left there. So oxaloacetate is the deaminated form of aspartate. And then aspartate then, is the aminated oxaloacetate. Okay. So once we take that amino acid, so we're in the cytoplasm here, we take the amino acid off of aspartate. This just leaves us with deaminated aspartate, which is oxaloacetate. So there, that's how we got that. That amino acid, though, went to the alpha-ketoglutarate, and it reformed glutamate. Okay, so alpha-ketoglutarate, I'll just write that again. Alpha-ketoglutarate plus an amino acid is glutamate. Just like in the mitochondria, oxaloacetate plus an amino acid is aspartate. So now we can see how all of this is tied together with our 6 player, the reversible reaction of 3, I should say. So aspartate, oxaloacetate to malate, and then backwards, malate, oxaloacetate to aspartate. But we also then have glutamate turning into alpha-ketoglutarate and back again as we are donating the amino acid into the main shuttle, the main reaction. So they're tied together. They are all dependent upon each other. Okay, so let's just reiterate that. We have gone over, it says the details here. We already did the details. So we're just going to go over it again, step by step, just to make sure that we are all on the same page. Don't look at this yet. I'll show you when we can look at that. Okay, so step 1. Step 1 was where we just kind of arbitrarily decided we're going to start step 1 at the oxaloacetate in the cytoplasm, taking the NAD, or taking the hydrogen from the NADH, leaving us with just NAD, and creating malate in the process. Okay, so we have taken the oxaloacetate, added that hydrogen from the NADH, and we have malate, and then we have NAD just left over. The whole reaction there catalyzed by a dehydrogenase. Remember, we've said that dehydrogenase enzymes are responsible for taking away hydrogens off of things, so that's what we did. And this specific dehydrogenase is malate dehydrogenase 1. So now following the product, we know that NAD is just going to go back and go back and be part of glycolysis, make more NADH. But the malate here, we're going to antiport with alpha-ketoglutarate. So malate goes in, alpha-ketoglutarate goes out. That's step number 2. Okay. Now step number 3, we're going to oxidize the malate. So we're taking that hydrogen away from the malate. Here's step number 3. Hydrogen goes away from the malate, goes to NAD+, giving us NADH, which can then go on to the electron transport chain. Okay, and because we've taken the hydrogen away from malate, now we have oxaloacetate again. Okay, so now we can go to step number 4. This is where those amino acids are going to become part of this system, where we are moving the amino acids around. So we're using an amino transferase. specifically aspartate amino transferase, and it's taking the amino acid away from glutamate and adding it to oxaloacetate. So what step number is that? Number 4. We are doing here, taking that amino acid off of glutamate, adding it to oxaloacetate. This is going to form aspartate. Glutamate, now that we've taken away its amino acid, is alpha ketoglutarate, so we use that in step number 2. Okay, now our aspartate is ready to be antiported out of the mitochondria to the cytoplasm in exchange for glutamate. So this is step number 5. So aspartate moving out, glutamate going in. Remember, aspartate has an amino acid on it, so it is taking an amino acid out of the mitochondria. For step number 6, now that we have aspartate back in the cytoplasm or out in the cytoplasm, we're going to deaminate it. We're taking away the amino acid using aspartate amino transferase to take away that amino acid. That amino acid is going to go to alpha ketoglutarate. So the amino acid from aspartate goes to alpha ketoglutarate. That makes glutamate. And leaving that aspartate deaminated, no more amino acid on the aspartate, which now it's just oxaloacetate again. Okay, so now we're back to, the end, which put us step number 7, which is really just like, oh, we're back to step number 1, because it's a big circle. Okay. Okay, now where this comes into play, this is just a picture of step number 3, where we take the hydrogen off of malate, add it to NAD+ to get NADH, which leaves us with oxaloacetate. So we can see that here. Here's malate. Here's malate dehydrogenase, which is going to take a hydrogen off of malate, give it to NAD+, so that we have NADH, leaving us with oxaloacetate. So that's step number 3. But remember, over here in step number 1, we did it in the reverse way. So we can also take that oxaloacetate. That oxaloacetate can take a hydrogen from NADH, giving us malate and NAD. So just to kind of show that we are just having these reactions happen this way in the cytoplasm and then backwards once we get into the mitochondria. Okay, a little bit more complicated than the glycerol phosphate shuttle. Okay. Okay, and here this is showing the relationship. So again, not really new information, just focusing in on a slightly different place. Here we are looking at the aspartate amino transferase enzyme. Okay, so here it's just showing the detail of how we take the amino acid right there off of glutamate. We're going to add it to oxaloacetate. So that is right here, what we're doing right here, step number 4. And in so doing, we will form aspartate. There's that amino acid. So we just had oxaloacetate, now it has an amino acid on it, rearranged a little bit, and we have aspartate. And then we have this, so just again to show you that we use different words for things all the time. This is just alpha ketoglutarate. So another name for alpha ketoglutarate. Let's just take that out. Okay. So there you can see that part of the reaction. So this is just an illustration of this. part here, taking the amino acid, adding it to oxaloacetate to form aspartate. That leaves glutamate behind without its amino acid, which is alpha-ketoglutarate. Okay, so that is the transamination part of this. And it can go in both directions, which we know because we saw it happening over here, right? So all of these things are reversible. And together they make a nice, neat little circle. The whole point of which, just to reiterate, to get that hydrogen off of the NADH, and with it its electrons, carry it into the mitochondria for the electron transport chain, replenishing in the meanwhile the supply of NAD+, so it can go pick up more electrons, more hydrogens from glycolysis, and then keeping our supplies of these molecules that are important for this transport shuttle mechanism, keeping them replenished, keeping them in the right place, so whether they are in the cytoplasm or in the mitochondria, so that the shuttle can just keep working around and around and around. Okay. Okay, and then here again, this is just showing again another detail, so no new information again. Here on this one, just zooming in on the specific part of the shuttle as taking the aspartate, or taking the amino acid off of the aspartate to reform oxaloacetate and adding that amino acid onto alpha-ketoglutarate to form glutamate again. So let's just kind of look at that one more time. It doesn't hurt to reiterate it because that is like a super complicated part right there and kind of difficult to remember with these amino acids for some reason. But just think of aspartate. It's going to lose an amino acid here because this is in the cytoplasm here. Okay, so we're not forming the aspartate, we're taking it away, we're breaking it apart when we're going to the right here on this direction. So the cytoplasm is going to the right. In the cytoplasm we are going to the right. The aspartate transaminase is the thing, the enzyme that is taking that amino acid off of the aspartate. It's going to put that amino acid, so I'll just put a little amino acid onto the alpha-ketoglutarate, and that is glutamate. Remember, glutamate is used to antiport aspartate out of the mitochondria. And then it's also used to aminate oxaloacetate inside the mitochondria. And once that aspartate has lost its amino acid, now it's oxaloacetate. So we are back, I should just leave this out, keep referring to it, we're back to oxaloacetate over here. Now the reverse, so if we were going in reverse, which you can see that this is a reversible reaction, this would be what would be happening inside the mitochondria. We're going in that direction instead, where we're taking the oxaloacetate, same enzyme, aspartate amino transferase, but this time it would be taking the amino acid off of glutamate, so it would be doing this part, using that amino acid to create aspartate, so oxaloacetate plus that amino acid will give you the aspartate, but in the meanwhile this glutamate lost its amino acid and it turned into alpha-ketoglutarate. So that is what's happening over here. So just kind of showing the relationship a little bit deeper between those amino acids and the main players, the malate, aspartate, and oxaloacetate. And then here is a picture of the whole thing with the enzymes and all that, showing our cytoplasm out here, intermembrane space, and then what's inside the mitochondria here. So going, kind of zooming in a little bit more on the entire reaction. Here we have malate. So we're inside the membrane space, the intermembrane space, we're inside the mitochondria. Here we have oxaloacetate. Here we have glutamate. Then we'll go down to aspartate. Don't worry about alpha-ketoglutarate for right now. Then over here we have aspartate. Again, ignore the alpha-ketoglutarate for a second. Ignore the glutamate. Well, we'll put the glutamate in here, the oxaloacetate, and the malate. Actually, let's just ignore the glutamate along with the alpha-ketoglutarate on this slide for now. We'll come back to it, so these are not permanent X's. We will come back to our glutamate and our alpha-ketoglutarate, but just focus on the malate, the oxaloacetate, and the aspartate. So our main things: aspartate, oxaloacetate, and malate, and we'll come back to glutamate and alpha-ketoglutarate. Okay, so here malate dehydrogenase, taking a hydrogen away from the malate, adding it to NAD+, and forming NADH that can go to the electron transport chain, which is on the inner cell or in the inner mitochondrial membrane. In the process, we form oxaloacetate. The oxaloacetate, if you followed along, is going to turn into aspartate. Now, what we saw on our picture here, this would have then gone out. So the aspartate would go out in exchange for glutamate. I try to ignore glutamate. I can't ignore it for long, but there we go. And then we would have our whole oxaloacetate back up into malate and NADH, NAD plus. So this is almost like just a mirror image of what we were looking at here. So it's just a flipped version. This is the outside. So here's the cytoplasm on the left. Here's the inside of the mitochondria. On this picture, the cytoplasm is on the right, and there's the inside of the mitochondria. So we've been looking at the, this outer mitochondrial membrane, but we haven't really been looking at what's going on inside the matrix. And remember that the Krebs cycle is happening here, inside the matrix. Okay, and the Krebs cycle also involves, we'll just put our alpha-ketoglutarate over here, and our oxaloacetate. These are also part of the Krebs cycle, right? So these are tied to the Krebs cycle. So what we saw here, the circle, we're getting that NADH, the hydrogen from it, and taking it into the mitochondria. That's happening right here. Okay, so here's that circle. And then here we go into the matrix as well. Okay, so it's the same thing, the same way. It's a cell membrane with the same process of getting those things across the membrane. So aspartate being antiported with glutamate, so moving across the inner mitochondrial membrane, just like we did on the outer mitochondrial membrane, same thing. Out here on the outer mitochondrial membrane, we had malate moving in and alpha-ketoglutarate moving out. So that's the antiporter there. So we have that out here on the outer membrane. We also have that in here on the inner membrane. So it's just a repeat of this shuttle happening again on the inner or in the inner mitochondrial membrane, so that we can get the whole process inside the matrix where we have the Krebs cycle, we have the electron transport chain on the inner cell membrane. So once you understand the shuttle here, it's just going to happen exactly again in the same way over here. All the same players, all the same carriers, all the same enzymes, molecules, everything is the same. The same with the transferring of the amino acids, all happening over here between glutamate and alpha-ketoglutarate, and aspartate and oxaloacetate. Transferring the hydrogen electrons between malate and oxaloacetate and NADH, so that we can have hydrogens from NADH on the electron transport chain. Okay, so that is the malate aspartate shuttle, and that ends our video about the malate aspartate shuttle.